Uh, Good evening and welcome to this NPTEL PMRF session on the course of Signals and Systems. Myself, Shouharda Ghosh, a second year PhD research scholar at the Department of Electrical Engineering, IIT Gandhinagar. So today, so systems. This is week 2. Alright, so what has been covered in this week? First of all, we have covered continuous and discrete time systems. Continuous and discrete time systems. Next, even, odd, and periodic signals. Third, orthogonality of signals. Then we have also covered shifting and scaling of signals in continuous and discrete time. Then the brief notion of signal and noise was introduced. Okay, so first we shall be covering a few of the questions that has been asked in the previous year's assignment, and then I shall revise all the concepts that have been covered in this week's lectures. Okay, or rather I would say that while covering these each of these problems, I shall be revising the concepts that have been taught in this week's lectures. Okay, so the first question says, determine the period of the signal sin t times sine of 2t. Okay, so first of all, whenever we are asked to check the period of a signal, what is the condition for periodicity? So whenever we have a signal xt, so it's said to be periodic if and only if, when we say if and only if, I write I double f x of t plus capital T is equal to x of t for all time belonging to the range of real numbers. That means the entire time axis, which ranges from minus infinity to infinity, and capital T is a real number which is greater than 0. Okay, so that's the fundamental condition. And when we have multiple signals xt, say xt is x1 of t plus x2 of t plus so on till xn of t, let's say each of them are periodic with t1, t2 and tn. Okay, so now what is the period of the composite signal? I mean, when you sum up all the sine, let's say sine signals together, what will be their period? So basically, first and foremost, we need to check whether ti upon tj for all I 1 I j I not equal to j. That means we have to check this ratio ti upon tj for all possible values of I and j ranging from 1 to n. That means, let's say I have t1, 2 and 3. So I'll check t1 upon t2, t1 upon t3 and t2 upon t3. Okay, so I should check all these ratios and see whether all of them are rational numbers or not. If it's no, then the signal is aperiodic. If all of them are rational numbers, then the signal is said to be periodic. And what is the net period? The net period will be the lowest common multiple or the LCM of T1, T2, all of them, okay, T1, T2, all the will T of n will find the lowest common multiple. Okay, so let's start with the same algorithm with this signal. So whenever you see any product of sines or product of cosines, always try to bring them back to the summation. Okay, so when we have sine t times sine 2t, what will we do? We'll use the property 2 sine a sine b equals cos of a minus b minus cos of a plus b. Utilizing that, I take the 2 outside, a half of, so it will be cos t minus 2t minus of cos t plus 2t. Further simplifying, half cos 2t, half cos 3t. Okay, so what are the individual time periods? T1. So actually cos or sine, whenever we write them on the form cos omega naught t, and its individual period is capital T equals to 2 pi upon omega naught. Okay, so here T1 is 2 pi upon 1, that's 2 pi radians per second. Then you look at T2, that's 2 pi upon 3 radians per second. Fine, now we have only two time periods to check. So if I look at the ratio T1 upon T2, that's 2 pi divided by 2 pi upon 3, and that's 3. It's a rational number, so we can easily find the period. And what's the period? The period is the LCM of 2 pi and 2 pi upon 3. So what is this? It's a fraction, it's a multiplicative fraction, so that's 2 pi seconds. So the period of our signal provided is 2 pi seconds. As you can see, if you substitute t by t plus 2 pi and 2t as 2 of t plus 2 pi, then you will get back the same signal. Okay, so I hope this is clear. Let's move to the next question. Question number 2. If xt is the Dirac delta let me check once whether the recording is going or not. Yeah, fine. Oops, sorry. So if xt is Dirac delta function, then what will be x of t upon 2, or what will happen with x of t upon 2. So your options are A, no change, B, area gets halved, C, area gets doubled, and D, dies to 0. So this is actually a question that pertains to the property of the Dirac delta function, which we learned in the previous week. Okay, and so what was that property? The property was delta of at is 1 by modulus of a delta t. And what was the second property? The integral of the Dirac delta function over the entire time range is 1. That means the area under the Dirac delta function is 1. So now what are we doing? Our xt is delta t, which implies x of t upon 2 is how much? Delta t upon 2. So what is the new area? Ax. So what can we write? We can write delta t upon 2 as half delta t dt, and based on this equation, that's simply there's a mistake over here. It's a is 1 upon 2, so it will be 1 upon half of delta t, and using the thing that I mentioned over here, I get this as 2. So our area increases from 1 to 2, so our area gets doubled, and hence the correct answer will be option C. Okay, if you have any doubts, you can type in the chat comment section and let me know. Let's move on to question 3. The period of a discrete time signal cosine of n upon 2 is okay. So we are given a discrete time cosine signal, and we are supposed to find this corresponding time period. Okay, so note that for a sine, or let's say cosine omega naught n plus phi, the time period is given by t equals to 2 pi upon omega naught. But note over here that this is a discrete time signal. And what does that mean? It means that the arguments inside this can only and only be integers. They cannot be rational. They cannot have the fraction parts. They can only be integers. Okay, so and why is that so? Because discrete time signals assume values only at indices like this, -1 1. So a typical discrete time signal may look like this. And how do they originate? They may originate from continuous time signals. Okay, let's say this is a continuous time signal x of t, and what do? We do something called sampling. That means at every sampling period capital T, we take the values. So x of n is actually x of, okay, so let me give the subscript a for x of c of t, x of ct, c denoting the continuous time signal. So this is continuous time or ct. And how when we move to discrete time, how do we get it? X of discrete discrete time xd is xc of nt. How can we visualize that through our diagrams? So let's say this was our continuous time signal, and when we need to capture the discrete time signal at time instant 0, I captured this. At time instant t, I captured this. At time instant 2t, I captured this, and so on and so forth. We keep on capturing these signals. And as a result, what we end up getting is this. We remove the time index once it moves into the discrete domain. We forget the notion of sampling period, and okay, so let me remove the impulse sign for now. If we use impulses to sample this, we call this impulse sampling, and we may study that in later portions of the course. And so this is our x of xd of n, discrete time. And sometimes it's not necessary that you will get discrete time. Okay, so let me write down the notation. Discrete time, which I'll call as dt later. We may not always obtain discrete time signals from the continuous time signals. Rather, they can be generated from the computer. So when they are generated from the computer, there is no underlying continuous time signal involved. It is just that you are storing the data in the form of arrays, and the array elements are being accessed one after the other. Like, let's say you have allocated a bunch of memory space for an array. Let's say the array name is x. So you have x of 0, x of 1, x of 2, okay, and so on till x of 10. And these are actually stored in memory location. Let's say f f f a f f f b, so on and so forth. So you can use that binary or hexadecimal numbering to access the memory location. Fine. This is an alternative view on how we obtain discrete time signals. So now getting back to the period of a discrete time signal, as I mentioned earlier, that the arguments, as you have seen over here, are supposed to be integers. Okay, so when we have a discrete time system, say cosine type signal omega naught n, okay, so when we shift it by n samples, we want it to be the same, naught n plus omega naught capital N. I would rather say it's not the arguments that is integer, but n that is an integer. Okay, please forget this confusion. It's actually the index n that has to be the integer, but not the argument. So cos omega naught n plus capital N. Okay, so note very much that this capital N has to be an integer, otherwise you can't add a fraction to an integer index. So what do you want? We want it to repeat, and in order to allow this repetition to hold, we have omega naught n equals to 2 pi. N has to be 2 pi upon omega. Fine. This is the time period. The time period is also an integer. And what does it mean? It means that omega must be a valid rational multiple of pi. Okay, so for example, if we have cos 3 pi by 7n, what will be its time period? So we have n equals to, let's say we do initially 2 pi by 3 pi upon 7. So we get 2 by 3 times 7, that's 14 upon 3. But actually we want to get n as an integer. Okay, so what will you do? In order to get n as an integer, we will try to ensure that we multiply n by some certain numbers, okay, so that we get an integer. So rather than 14 by 3, if I have 3 14 by 3s, that gives me 14. Okay, we'll try to convert this rational number into a real number by multiplying the smallest possible number. So you see, n is, that means 14 is the same time period. So let me verify this. That's because 3 pi by 7 n plus 14, that gives me cos 3 pi by 7 n, 7 2s are 14, so 6 pi. So 6 pi is 3 multiples of 2 pi, so it's still the same. Now we were given the signal cosine of n upon 2. As you can observe that this omega is half and it's not a rational multiple of pi. Okay, so what does it mean? It means that this sinusoid is aperiodic in nature. This sinusoid is aperiodic in nature. Okay, I hope this is clear. Now moving on to the next question. If x of t is a sawtooth signal with a period of 1 nanosecond, what will be the period of x of 5t? Okay, so now first of all I need to understand that this information is redundant. Okay, why? Let me show you. Okay, so before we move into the periodicity of the signal, let's look at signal scaling along time axis. Okay, so let's suppose, let me take a finite duration time signal, so minus t to capital T. Okay, so when we scale it to, let's say, x of 80, what does it become? For our convenience, let us write it as x1 of t. x1 of t is x of a upon t. We observe that this signal is 0, x of t is 0 when t, magnitude of t is greater than t, right? So now let's check for x1 of t. In this case, we also want to ensure that the signal remains conserved. So what do? We put this argument at modulus is greater than capital T. So what does that mean? That for this signal to be 0, it should happen for mod of t greater than t upon a. So how would it look like? Okay, so there are two cases. Case 1 where a is greater than 1. Okay, so when, and I'm assuming that a scaling factor is a positive number. So if a is greater than 1, this is minus t this is t. Let me draw my original signal for the sake of completeness. So if a is greater than 1, t upon a will be less than 1. So let's suppose our t of a something looks like this. So our signal will look something like this. And now if a is less than 1, then our signal stretches more than, oh sorry, I should have, yeah, it's correct. So it moves out. So as you can see, the signal has stretched out. Okay, so this a greater than 1 case, I should write it in the color in which I have drawn. So for a greater than 1, we have something called signal compression, and for a less than 1, we have something called signal expansion or stretching. Okay, very simple. So we have x of 5t, and here a, which is 5, is greater than 1, which means that the signal is compressed. Okay, so let us assume any arbitrary waveform which has a period of 1. So our xt repeats every 1 nanosecond. So let's have this. So it's 0, 1, 2, 3, 4. Now when we make it x of 5t, what do we have? It will repeat. 1 will become 1 upon 5, 2 will become 2 upon 5, 3 will become 3 upon 5, and so on. So the period over here was 1 nanosecond, and the period over here is 1 upon 5, which is 0.2 nanoseconds. So as you can very well see over here that the sawtooth signal was just a gimmick. The main thing lies in the period of the signal. Okay, so I hope this is clear and there are no doubts. Fine, and through this we have explained the signal scaling concept. Now let's look at question number 5. If xt is sine pi t and yt is cosine of pi t, we can write yt as x of t plus b. So now we need to find b. This is a concept of signal scaling. Okay, so in such questions what we do, okay, yt, which is cosine of pi t, okay, we have to write this as a shifted version of x. Now what are the properties that we know about cosine and sine? We know that cosine of theta is sine of let's say theta plus pi by 2, isn't it? Very simple. Theta is in the first, theta gets shifted to the second quadrant, sine remains positive. So what do we write? Sine pi of t plus pi by 2. Okay, now further taking the pi outside, I get t plus half. And so what is it? Our x of t is sine of pi t. X of t plus b is, directly substitute t plus b into this. Okay, understand that this is not equal to sine pi t plus b. You are actually substituting the entire argument into this capital, into this small t. Okay, so you can easily notice b is equal to half. So this is the answer. And to look at the concept involved, let's look at any simple signal xt which lies between 0 and capital T. Okay, so if we want to delay a signal, let's say by a quantity tau, what we do? We subtract tau from it. So you subtract and it moves right. Actually, it's a bit counterintuitive for those who are learning signals and systems for the first time, but if you keep this in mind, it will be a bit easier. Or if you are finding it difficult, then let me tell you another way. Whenever you see some delays or shifting done to a signal, first define an alternative signal x1 of t and write it equal to x of t minus capital T. Okay, now you see the important points of the signal. What do we mean important points? So the points where the signal starts, points where the signal stops, points where the signal goes maximum. Okay, so like if you have some kind of a signal like this, right? Okay, so what are your important points? Your important points will be the starting point, this edge when the shape changes, this edge where is a jump, this edge where is in a fall, another edge where there is a starting, another edge where is a slope change, another edge where it completely stops. Okay, so these are your critical points. Okay, so what you can do, you map these critical points. So you have to map from this to this x1 of in order to make things t minus tau, that means this argument should be equal to your critical point. Okay, so equate this to your critical point. T equal to minus tau, it's 0, so the corresponding t will be 0. So for this x1 of t equals to x of t, for this time you will have capital tau. Okay, so even you may get confused by multiple small t's, so let me use the notation z for simplicity, so that those who are watching it for the first time get understand things better. So x1 of z is x of t minus tau. Fine. Now what do we want? We want the critical points corresponding to this argument. Okay, so we want x1 of z is x minus z minus tau. Okay, z minus tau equals to 0. Okay, so z will be equal to tau, z minus tau, this our first critical point, tau is t, z will be equal to t plus tau. So what are critical points? Tau and t plus tau. So you note them, tau and t plus tau, and once we have the z, you can back substitute it by t, tau plus t. So you see the signal which started from z is now starting from tau. Okay, it is called delaying, and this can actually be an explicit property of real life systems. whenever you look at any signal, whenever you transmit a signal, there has to be, you encounter delays whenever you process your payments, you encounter delays whenever you go shopping, you encounter delays whenever you call over the phone, you encounter delays in every system, be it electrical, mechanical, chemical. Okay, delay is an intrinsic property, so these are realizable systems. But let's say you advance a signal, advance by capital tau. How does it look? X of t plus capital tau, and in all our conditions we are assuming tau is greater than 0. So how does it look like? So once again we take our old signal, and now when we shift it back, we go backwards. What will we do over here? Let us again use that policy. X1 of z is x of z plus tau. Note our critical points 0 and t. Z plus tau equals to 0 plus z equals to minus tau. I take minus tau over here. Z plus tau equals to capital T, so z equals to t minus capital tau. So let's say t minus capital tau is over here, assuming it's negative. Okay, so what do you have? I have a signal which initially was supposed to start at 0, and in a t it starts before it originates. Okay, so a signal was supposed to start at 0, it started at tau minus tau before the original signal was created. So such systems are since I'm talking in time domain, such systems are non-realizable systems. You cannot have you cannot have systems giving you outputs before they even occur in reality. Okay, so these are non-realizable systems. Okay, so that was advancing, and this one, this x of t equals t plus b, here is, you note, this is a advancing of signal. So what I've explained over here is a simple division of shifting of signals. Okay, and all of these discussions as of now has been done in continuous time domain. Moving on to the next question. Question number 6. We are given two signals. Xt is 1, 2. That's 1. Yt 0, 1. So we are asked what is the relationship between yt and x of t. So we have to write yt in terms of x of t. So how do we write? Okay, so as you can see, 1 has moved to 0, 2 has moved to 1. Okay, so what is happening? This is an advance by how much? 1. And if you want to generalize it for any arbitrary signal, how should I map them? Then you should have two axes, time t and time z. In time t, you note the critical points for your signal. The critical points are at 1 and at 2, and at time z, you note corresponding to that shape, you note the shifted critical moments 0 and 1. And when you have such a table, you can easily find the linear relationship between t and z, right? So for this case, z is simply how much? T minus 1. Y of z is 1. And what is z? z equals t minus 1, so t equals to z plus 1. So what is this equal to? X of z plus 1. Okay, now back substitute the variables. By back substitute I mean replace z by t. You have x of t plus 1. That's it. Then we move to another question. Question number 7. We are given xt. Xt starts at 1, z2, 1 t, yt starts at 1 upon 3 and z 2 upon 3, so this is 1. So let me write t and z table. We have a critical point at 1, correspondingly it's 1 upon 3, critical point is 2, correspondingly we have 2 upon 3. You note very well over here that the width was 1 and here the width is 1 upon 3. So what are we having over here? We are compressing the signal in time domain. Okay, from that perspective I say it's a compress by 3. So when we have a compress by 3, we can easily write yt equal to x of 3t. Okay, our a factor here is greater than 1. Fine. Now let me go to the alternate approach. Z equal to t upon 3. So t is equal to 3z. Now substitute it as x of 3z, or it becomes x of 3t. Okay, so that's our signal. Fine. So I hope you have understood how is this taking place. Now let's move to another question. You are given the signal x of t that starts from 1, becomes 2, and then ends at 3. That's amplitude 1. And then you have y of t starts from 0 to 1 upon 3 and z 2 upon 3. Amplitude remains the same. Again the same thing. Let us note the critical values t and z. T is 1, 2, 3. Here it is 0, 1 upon 3, 2 upon 3. So let me choose, we have a linear transformation, so let me choose two numbers to have this line of linear equation. So z minus 0 upon t minus 1 is how much? Is equal to the slope 1 by 3 minus 0 by 2 minus 1. Okay, so these are 2 points on a number line, so I'm kind of doing fitting the line and I'm trying to find the slope of the line. Z upon t minus 1 is how much? 1 by 3. Three z equals to t minus 1, and we have t equal to 3z plus 1. So what do we do? Xt becomes x of 3z plus 1 and replace z by t, x3 t plus 1. Okay, so I hope it's clear. So let me for betterness, let me write an algorithm for that. So tabulate all critical points for xt at t and for yt at z pairwise, obtain a relation which is obviously linear between t and z such that you write t as a function of t is equal to az plus b, something of that form. B may be positive, negative, a may also be positive or negative. So now what we do this transformation. X of t gets replaced by x of az plus b, and you substitute, replace z by t, and you get x of at plus b. That's it. This is the property, or not the property, this is the algorithm to find relation between xt and yt. Okay, so I hope this is clear to all. It will be very easy and helpful in your exams. Fine. So yeah, now let's move to discrete time systems. So you are told that if xn is non-zero, I mean these have the entries 0.5 at 1 and 2, and at 3 and 4 I have 1. Now the same, when you get the output yn, it is all zeros. Okay, all of them are zeros, and in this case also, except 1 2 3 4, the rest of the entries are all zeros. Okay, fine. So if I have to write this in set notation format, so what we do, we write it as, so at the 0 index we have 0, and when we mark that, we give this arrow sign. Whenever we give this arrow sign, it means that it is the entry at the 0th index, n equal to 0. 0.5 0.5 1 1, and when you stop it, it means that rest left and right of this array are all filled with zeros. And yn, we can simply write it as 0, which means our left and right are all zeros. Fine. So now you are supposed to relate between yn and xn, but unfortunately this is a discrete time system, and what happens is that in discrete time system there is a loss of information, and there can be multiple ways in which you can obtain yn from xn, one of them being yn directly being multiplied by 0. So in such cases, you should also always look into the options that are provided in your question. So in this case, the options that are provided are a, yn equal to x of 4 upon 3n, then you have provided yn equal to x of 3 by 2n, yn equal to x of 5 upon 3n, and the please give me a moment. Oh, thank you. So this fourth option is yn equal to x of 4n. Okay, so in this case actually there's no way other than checking each and every option and drawing them. So what's y of n? That's x of 4 upon 3n. So we'll look at the indices. Y0 is x of 0, which was originally 0 over here. It's matching. Y of 1 is x of 4 upon 3. Unfortunately, x of n, the argument is defined only for integer numbers. So x of 4 upon 3 does not exist. So it's 0. Yeah, so it's an important point. So whenever you are dealing with such xn, yn kind of numbers and the argument, that means x of something, if that comes out to be not an integer, okay, so if it's not an integer, substitute its value with 0. That means you have lost the information. Then y of 2, that's x of 8 upon 3, that's still 0. Y of 3, that's x of 4. So what's x of 4? That's 1. So our signal will look something like this: 0, 1, 2, 3. Okay, at 3 you have 1 and rest everywhere 0. So you see over here it doesn't look like yn. Yn is all zeros, so it's incorrect. Now let's look at yn equal to 3 by 2n. Y0 is x of 0, same. Y of 1 is x of 3 upon 2. This is a fraction, so it's 0. Y of 2 is x of 3 and x of 3 was 1. That's 1. Y of 3 is x of 9 upon 2. That's 0, and furthermore you get zeros. So the signal looks like 0, 1. At 2 it jumps up to 1, and here you. So it's once again non-zero, and you miss this out. Now you check this out: x of 5 upon 3 n. Okay, so y of 0 is the same. Y of 1, x of 5 upon 3, it's a fraction, so it becomes, sorry for that, 0. Y of 2, x of 10 upon 3, that's still 0. Y of 3, that's x of 5, but note over here, as I told you earlier, everything outside 4 and less than 1, are still zeros, right? So it's a 0. So, and if we go further and further, we'll get all fractions, and whether it's not a fraction, then we see that it corresponds to x of n becoming 0. So you see, this is the only option which boils down to all zeros, and hence this is the correct answer. For the sake of completeness, let me check yn equal to x of 4n. Y of 0 is 0, because that's x of 0. Y of 1 is x of 4. What's x of 4? X of 4 is 1. Y of 2, and so on. There will be multiples of 4 at which xn is 0. So how will the signal look? At 0 it's 0, at 1 it's 1, 2 is 0, 3 is 0. Okay, so rest everywhere it is 0. So this is also wrong, and we have shown. Okay, so for now we have completed the previous the year 2022's assignments have been revised over here, but in the process we have not covered certain concepts. I have not revised some concepts, so I will revise them over here. And if you have any doubts, you can ask me before I close this session. Okay, so even signals, even and odd signals, even and odd signals. Okay, so whether it is any any continuous time or discrete time signal, let me deal with the general continuous time case. X of t, what is the condition for it to be even? The condition for it to be even is the negative time axis x should be equal to the positive time axis x. That means it should be, it's called symmetric. And if it's odd, what is the condition? The negative axis should be the opposite, the reversed, the flipped version, negated version of the positive axis. Some very simple examples which illustrate this. This is an even signal and this is an odd signal. Okay, it's not looking good. Let me make it look good. Okay, so this is an odd signal. As you can see, it's anti-symmetric. It should be -1. And there are signals which are neither even nor odd, so they don't satisfy any of the properties that have been shown over here. Okay, for example, as you can see, the left half is a curve and the second right half is a triangular wave. Okay, so in general, any signal xt can be written as the sum of an even signal and an odd signal. Okay, even and odd. So how do we write the even signal? The even signal xc of t is half xt plus x of minus t. Okay, and the odd signal xo of t is half of x of t minus x of minus t. Now you can very easily show that these are actually even and odd signals. If you try to find out xc of minus t, it will come out to be xo of t, and if you find out xo of minus t, it will turn out to be minus xo of t. All right, so now let us solve a question that asks us to find the even and odd portions of a signal. Okay, so these are self-practice questions which I am creating on my own just now. Okay, but these are very common questions which you may find in your semester exams or maybe your assignments or even GATE exams or such PSU or competitive exams. Okay, fine. You have the signal at -2, -1, 0, 1, 2. Okay, and let us choose the amplitudes. It's 1 over here and 2 over here. That's x of t. Now on the same line, let me draw x of minus t. So what will I do? I will flip them. So this is called reversal or flipping. So what we did was scaling up or scaling down in the time domain, okay, or shifting. So here what will happen? You will just flip it like a mirror image. Like here 2 will become minus 2, 1 will become minus 1. So in 2 you have a rise from 0 to 1. So in minus 2 you will have a rise from 0 to 1. Here from 2 to 1 you are staying along 1. Here from minus 2 to minus 1 you will stay along 1. Here at 1 you are rising up. At minus 1 you rise up over here. 1 to 0 you stay at 2. 1 to 0. Minus 1 to 0 you stay at 0. Here is a fall from 2 to 0. Here is a fall from 2 to 0 at 0 index. At 0 index. So you may find it repetitive, but I am saying this, emphasizing this if you are learning signals and systems for the first time, okay. And here from 0 to minus 1 is a repetition. 0 to minus 1 you move up. So here you move up from 0 to 1 and you move up over here. Similarly you move up over here, and then I can draw this 2, 1 and 2. Okay, now let me try to break this into various segments. And these segment breakings are being done for the sake of simplicity, because we will be doing addition and subtraction. So there are 4 segments, 1, 2, 3 and 4. Let me increase the okay. So when I add region ones, so it's 2 over here and it's 1 over here, right? So 2 plus 1 gives me 3. So when I add from minus 2 to minus 1, I will have a rise. In both cases there is a rise, and will be 3. And then there's a fall. There's a fall from 2 to 1, and there's a rise from 1 to 2. So the 2 cancel each other and will remain at 3. And if I subtract them, x of t minus x of minus t, so I do 2 minus 1, okay. So it's 2 over here and 1. So I subtract 1 this from this, so it will be a minus 1. Sorry, not a minus 1. So minus 2 minus 1, it will be 1. I am doing this because I want to put the odd and even parts together. Second power portion, addition. Initially this is at 1, this is at 1, and this is at 2, so I stay at 3. And over here you see I am at 0 and here is at 2, so I go at 2. But at this point is a fall at 0 as well. So you see there's a 0, it's fixed at 0. It initially stays at 2, so I will fall from 3 to 2, and there is sudden jump to 0. Because of the sudden jump I will I have 0 plus 0, that's 0. So there's a, and that is at index 0. So I go from 3 down to 2 and a sudden fall at 0. Okay. So I hope this is clear. If there are any issues, please type in the chat box. Okay. Now we look at the subtraction. So this is 1 over here. This is 2 over here. So 1 minus 2, that's minus 1. Here it's a 0. Here it's a 2. So 0 minus 2, that's minus 2, okay, and minus 2, and now we have a 0 and a 0, 0 subtracted with 0 because of the sudden fall it becomes 0, okay. So we till now we have obtained the left half of the uh, odd and even portions. So let's plot that out for now. Xe of t minus 2 minus 1. So initially it was 3, and from 3 we go down from 2. So initially it was 3, and from 3 we go down to 2, and then it falls down to, okay, we keep it over here. And once again at x, for the odd version of t, from minus 2 to minus 1, we initially stay at 1, and then from minus 1 we drop down over here 1 down to minus 1, and which comes further down to minus 2. So here it's a minus 1 and here it's a minus 2. Okay, now we will not resort to any addition further. We will use the properties of Xe of t. So what were the properties? An even signal is symmetric around the vertical axis. So you see over here, we simply mirror it around, then you obtain the even signal. And for the odd signal, we go up, we flip it up, I mean NT. So here it goes down, here it goes up. It goes from minus 2 to minus 1. Here we will go from 2 to 1, and it falls down from minus 1 to 1. So we'll fall down from 1 to minus 1, and then this rectangle 1 2 t. Okay, so this is the even part of the signal and this is the odd part of the signal. So I hope you have understood how to decompose the even and odd parts of a given signal. Our original signal was over here, and we have obtained the corresponding even and odd parts. Okay, so let me so we are done with the even and odd portions of a signal. Then we shortly mention about something called orthogonality of signals. So as you might be knowing, for any vectors v1 and v2 which belongs to the n-dimensional space, let's say of real numbers, you can also have a vector of complex numbers, okay, so they are said to be orthogonal if their inner product is 0. Okay, so what does it mean? That element by element, if I multiply them, I get 0. In a very other words, you write this, okay, so that means that there is no connection or correlation between them. Similarly, this is for the vector space, elements in a vector space. Similarly, when we have functions in real time, they also form something called vector space, but it's out of convention, it's out of the scope of discussion in this course. But if you have studied linear algebra, and if you go through much more detailed studies in, say, signal processing, then you might be knowing, or you will be knowing, that functions, real functions, also form a vector space in themselves. You must forget the notation that vectors only refer to the so-called three-dimensional coordinate system where you used to draw forces and other stuff. So that those are one kind of vectors, but vectors, even scalars are vectors by themselves. If you study vectors properties, then their properties like additivity, commutativity, belongingness to the vector space, linear combinations. Okay, so once any set of elements that satisfy these conditions are said to be vectors, and our real continuous time signals are one of them. Okay, so they also, and for every vector space there is something called the inner product defined for every vector space. So when we say that this inner product is 0 or they are orthogonal, we say that they are orthogonal when the integral f1 of t f2 of t dt is equal to 0. Okay, so what can be one example? The simplest example is sine omega naught t and cos omega naught t. Okay, if you integrate them over their period, 2 pi upon omega naught sine omega naught t cosine omega naught t dt, they will turn out to be 0. And this is a very useful property which we'll be using in the upcoming upcoming lectures on Fourier series, Fourier analysis. Okay, so as you and remember, when you learned vectors, so your fundamental vector spaces axis I cap, j cap and k cap, they were used to write, they are the something called the orthogonal basis. Okay, so these orthogonal bases were being used to write other vectors. Other vectors were written as a linear combination of these orthogonal bases. Similarly, when you will be learning your Fourier series, you will be using such orthogonal set of functions. Okay, so and then what we will see, we will learn that signals can be written as orthogonal summation of orthogonal functions. Okay, not extending the discussion to this now. Okay, so this is your signal x of t, and what you are supposed to do is let's say you are supposed to find minus x of t upon 2 plus 5 upon 2. How do we do that? This is an even simpler question. Look at the critical points -2, -1, 0, 1, 5. Okay, so when you have t and you have minus t upon 2 plus 5 upon 2, fine. So we note down these critical points over here and calculate their values. So let me take a calculator with me. 2 plus 5 by 2, this is turns out to be 3 upon 2, this turns out to be 2, this turns out to be, okay, so I think I made some mistake over here. It should be 7 upon 2, this should be 3, this should be 5 upon 2, this should be 2, this should be 0. Okay, so now See, all of them are in the positive. 0, 1, 2, 3, 1, 2, 3. This is 5 upon 2, 4. This is 7 upon 2. This is 5 upon 2. Okay, so so when we move from 1 to 5, it moves downwards. Now we are moving from word 1 to 5. When we okay, so let me do it clearly. We are moving from 5 to 1 upwards. You see, 5 to 1 means moving upwards. So in that case, we're moving from 0 to 2 upwards. 0 to 2 I move upwards, and then at 1 I have a fall like this. So at 2 I will also have a fall like this. Repeat, from 1 to 0 I go down, 1 to 0 I go down to 0. So 2 to 5 by 2 I will also go down to 0. So although this transition is very steep, now from 0 I have a rise. So at 5 by 2 I will also have a rise. Now it moves constant by 1 minus 1. So 5 by 2 to 3 I will also remain constant, and here it again moves down to minus 2. So this movement will be shown from 3 to 7 by 2. Okay, 1, 2. Okay, so now you have also seen the other way around, that if you are given some transformation, how will the signal look like. Okay, so I hope all the concepts related to these covered have been that have been covered are clear to you. And okay, so are there any questions from anyone? Please type in the chat box. Okay, so I assume that none of you have doubts and are clear with everything presented. So I am closing the session over here. Goodbye. Thank you. Wish to meet you in the next session as well.